Welcome to Center of Math's series on unusual properties in math. Today we're going to talk about two examples. A function which is bounded, a bounded function having no relative extrema on a compact domain, and a function which is only continuous at the irrationals and discontinuous at the irrationals. First, we want to know one thing. So if we look at some interval AB and all rationals in this interval AB of the form m over n, m and n are some integers. So note if the set of all n, m, and n are relatively prime, note if the set of all n, all possible n in this interval is bounded. Note that, in fact, if we look at this bounded set, then we'll have a finite number of different n's. And so since we have a finite number of different n's, only so many expressions of the form m over n fall between this interval AB. And so we're going to have a finite number of rationals in the interval AB, which is not true. So since we have infinite rationals in any interval in the real line. So this tells us that n, in fact, is unbounded. So we can find in any neighborhood of a point, we can find rationals of the form n over n, where n can be as large as we want. So we're going to use this. So we're going to have a function. F is defined on the compact set, the closed interval 0, 1, and it's going to R. F of x equals minus 1 to the n times n over n plus 1, where x equals m over n, m and n are some integers, m and n are relatively prime. And if x is irrational, f of x equals 0. So this function, so it's bounded clearly, n over n plus 1. It's always absolute value between 1 minus 1. This is defined on a compact domain, and it has no relative extrema because this always approaches and gets as large as we want in any neighborhood of a point. So it gets as close as we want to minus 1 or plus minus 1 in any neighborhood of a point, but it never actually reaches those points. So it has no actual relative extrema in any any neighborhood anywhere on this domain. So an example of a function which is only continuous at irrational points and discontinuous at rationals, which a function defined on the real numbers to the real numbers. Define f of x equals 0 if x is irrational, and 1 over n if x is a rational number, the form m over n, where m and n are relatively prime. So again, using the fact that in any neighborhood of a point, we have n can get arbitrarily large, and also the amount of n's whose absolute value is less than some given number, it's finite in any neighborhood. So around any irrational point, we can take a neighborhood smaller and smaller, so that the lower bound of n will in fact get bigger and bigger. And so the value of the rational points will get smaller and smaller in this neighborhood. And so as we take a neighborhood smaller and smaller, we get the value of the rationals gets closer and closer to 0. So this is in fact continuous at their irrational points. And any of the rational points, because they're a value 1 over n, the irrationals are dense. So they're always going to be distance 1 over n from the irrational points, and so it's not continuous at the rational points. Thanks for watching. Please check out centermath.org, check out our blog, follow us on Facebook and Twitter. And if you like this video, please check out the rest of our unusual properties in math videos in our playlist. Thank you.